Welcome everybody. Let's talk about how we balance redox equations in acidic solution. When you have an oxidation reduction process occurring in a solution, oftentimes the solution itself gets involved in the reaction. And if you're in an acidic solution, there are extra hydrogen ions present. And so balancing these reactions can get a little complicated. So the easiest way I have found to do so is using a method called half reactions. Here's the process, and then I'm going to show you how to do this using two examples. So the first thing you're going to do is you're going to take your overall chemical equation, you're going to identify what's being oxidized, what's being reduced, and you're actually going to break that equation into two pieces. One half reaction that's for oxidation, and one half reaction that's for reduction. Once you have your two half reactions, you will balance each independently. You'll start by balancing elements other than hydrogen and oxygen. Then you'll balance the oxygen by adding water to the opposite side of the equation. Once you've balanced your oxygen, you'll balance the hydrogens present by adding H+ ions. Again, we're in acidic solution, so there are H+ ions all over the place. Remember, those are really hydronium, but for purposes here, we can just talk about a hydrogen ion because that's the part that will be transferred and get involved in the chemical reaction. Once you have balanced the hydrogen, the oxygen, and the other elements, you need to make sure that charge balance is still being observed, which means the total charge on the left side of your equation and the total charge on the right side of the equation must be equal. And we'll do that by adding electrons to the equation. Once you have done that for both half reactions, you will then add those half reactions together, but you have to make sure that you've got the same number of electrons being gained and lost in both equations. And so you might need to manipulate the equations to accomplish that. And then you're just adding them together. Let's take a look at how this works with our first example. In this example, we have the permanganate ion reacting with an iron 2+ ion to form iron 3+ and the manganese 2+ ion. This is a net ionic equation. It makes it simpler because we're only focusing on the things that are actually changing in this reaction. First step has to be to write the half reactions. And in order to do this, we need to figure out which chemical species is being oxidized and which chemical species is being reduced. So we're going to start by writing the oxidation numbers on every atom. Now, most of the atoms in this equation actually already have oxidation numbers on it because they are charged species. But in MnO4, there are two different elements, and we need to figure out the oxidation number of each of those. In this case, each oxygen has an oxidation number of -2, and since there's 4 of those, that gives us an overall oxidation number of -8 from the oxygens. In order to add up for the chemical species overall oxidation charge, oxidation number and charge to be -1, this means the oxidation number on the manganese has to be +7. At this time, now that we have oxidation numbers for every element, we can figure out what is being oxidized and what is being reduced. As you look at this screen, you will notice that the manganese goes from +7 to +2. Its charge is decreasing, or oxidation number is decreasing. It is gaining electrons to do that, thus this is being reduced. Meanwhile, the iron is going from +2 to +3. This is losing an electron in this process, and this is being oxidized. Once we have this identified, we're going to write our equation. We're just going to take the two chemical species, the left and the right, that were involved in that reduction and write them into a single equation. And we'll take the ones that were oxidized, the reactant and the product showing that oxidation, and it'll become a separate equation. So I have the half reaction corresponding to the reduction on the left. You have the MnO4- and the Mn2+. And then on the right, I have the half reaction for the oxidation, the Fe2+ and the Fe3+. We're now going to balance each half reaction. So you start by balancing elements other than oxygen and hydrogen. In this case, for the manganese equation, just manganese. One on each side, it's balanced. Then, for this same equation, we're going to balance the oxygens. There are 4 oxygens on the left and none on the right. So we're going to remedy that situation by adding 4 waters. By adding 4 waters to the right-hand side of the equation, we now have the same number of oxygens on both sides. That's great for oxygen, but it messed up hydrogen because now I have 8 hydrogens on the right-hand side of that equation. So I need to get 8 on the left. We'll do that by adding 8 H pluses. Since we're in acidic solution, there are hydrogen ions that are free and can get involved in the chemistry. At this time, the elements are balanced, but the charge is not. If you look, you will notice that on the left side of this equation, you currently have a total charge of +7. That is the -1 from the MnO4 and the 8 H pluses. Those coefficients are really important. So currently have a total charge of +7. On the right-hand side, my total charge is +2. Those aren't the same. So what you're going to do is you're going to add electrons to the side of the equation that has the more positive charge. And you're going to add enough electrons so that the charges on the left and the right side of the equation are equal. In this case, I need to add 5 electrons to the left side of the equation. Okay, my reduction half reaction has been balanced. It is good to go. Let's do the same for the oxidation one. This one's simpler. Iron is the only element present. It's already balanced. There's no hydrogen or oxygen, so all we need to do is balance the charge. In this case, looking at this, the left-hand side has a charge of +2. The right-hand side has a charge of +3. I need to add an additional electron to the side that is more positive, so I'm going to add it to the right-hand side of this equation. Adding that single electron fixes everything. Now I have 2 balanced half reactions. It is time to add them together. And so I'm going to stack them like we've been seeing our equations when we get ready to combine them in our previous units. The only catch is that before we can add these, we have to make sure we have the same number of electrons being gained and lost in this chemical process. Otherwise, we're going to be destroying or creating matter, and we can't do that. So looking at this, the top equation has 5 electrons being transferred. The bottom one only has 1. So we're going to multiply everything in that bottom equation by 5. At this time, we can add our equation, keeping all of the reactants on the left side of the arrow, all of the products on the right-hand side of that arrow. And then we can cancel any chemical species that are on both sides of the arrow, just like we do have done in the past. In this case, that's just the electrons. And what we are left with is our overall balanced chemical equation. Let's take a look at a second example, just to make sure that this process is making sense. Okay, in this case, I've got some phosphorus reacting with aqueous chloride ions to form phosphorus trihydride and chlorine gas. Again, we're working in aqueous solutions, so we know that we have water that we can add to balance equations and H+ that we can add to balance equations as necessary. But we still have to start by determining what's being oxidized and what's being reduced. So we're going to begin by writing oxidation numbers. This means that the phosphorus went from 0 to -3. It was reduced. Meanwhile, the chlorine went from -1 to 0. It was oxidized. So now that we've identified what's being oxidized and what's being reduced, we can break this into 2 half reactions, one for the reduction and one for the oxidation. So now that we've got our 2 half reactions, we're going to balance each one independently. I'll start with the reduction on the right. Phosphorus will need to be balanced, so I need to put a coefficient of 4 in front of the pH 3. And that means that my hydrogens are definitely not balanced, so I've got 12 hydrogens on the right, so we'll add 12 H pluses to the left. That fixes the hydrogen. There was never an oxygen issue, so now we need to address charge. On the left-hand side of this equation, the charge is a +12. On the right, it's 0. So we're going to need to add 12 electrons to the left-hand side of that equation. Again, you're adding electrons to the more positive side of the equation. That one's now balanced. Chlorine's going to be a little easier. I do need to add a second chloride ion so that the chlorines are balanced. And now I just need to balance charge. Because I have 2 Cl minuses, that's an overall charge of -2. I'll need to add 2 electrons on the right. Be sure to take into account what your coefficients are when you're balancing your charges. Now that the now that the half reactions have been balanced, it's time to add them together. So I'm going to stack them again. And then before I go any further, I'm going to make sure I've got the same number of electrons in both equations. I don't, so I'm going to need to multiply the bottom equation through by a coefficient of 6 in order to have 12 electrons top and 12 electrons bottom. And at this point, I can add the equations, canceling anything that appears on both sides, which in this case is the electrons. And thus we have successfully completed another balancing of a redox equation in acidic solution. So just to recap, and you'll get plenty of chances to practice, when you go to balance a redox equation in an acidic solution, the water and the excess hydrogen ions that are present in solution can get involved in the reaction. And so to balance it, you'll start by identifying what's being oxidized, what's being reduced, write two half reactions. Balance each half reaction independently, starting with elements other than hydrogen balancing elements other than hydrogen and oxygen first, then balancing oxygen by adding water as necessary to the equation, balancing hydrogens by adding H+ ions, and then balancing your electrons to ensure that you have conservation of charge on the left and the right side of the equation. Do that for both half reactions, and then add them together, ensuring that you have the same number of electrons being gained and lost in those two equations.